All right, we're recording. Share that. Wait, nothing better than trying to not sneeze in a microphone. All right. What have we got going on here? Last lecture today. Ordinarily, I wouldn't have this during the semester because of holidays and whatnot. But with the online stuff, holidays are largely irrelevant. And so I have this extra one I gave last semester in 111, so I'll do it again. All right, it's only 43 slides. So I'll go over, at the end, I'll go over some of the worksheet solutions. And then later in the week, I'll go over the rest of them. I'll schedule another meeting, which it would be optional. But I'll go over the rest of the worksheets. I have the other two to return to you as well. I just sent back a couple of them. They take a long time to grade, surprisingly. So I'll do another meeting later in the week, maybe Thursday or Friday, and I'll go over the rest of them and maybe mention something about the final. All right. What do we got here today? Material selection and design. All right, and this would be a chapter towards the end of the book I gave you. But material selection. All right. Now, at some point, a good chunk of civil engineers perhaps have to decide, what material do I pick for something? Right? The bridges are made of steel. What kind of steel? Right? There's different grades and all that, if you recall. What kind of concrete? What kind of cement do I want to make? Right? You know that all these materials exist, but how do you decide which particular one you want to choose? Right. Well, there's some logic behind that. A lot of it is largely driven by this fellow down here, Michael Ashby. And he has a whole bunch of books pretty much with the same titles. Material selection. Right? He has pioneered material selection and tried to make it logical and mathematical. All right. So materials, right? They have a set of properties, right? Or what he might say as attributes, right? And you know that we've talked about the properties, not all of them, but a good chunk of them. Materials have a particular strength characteristic, yield strength and tensile strength and hardness, particular density, and a particular cost. That's also a property, whether or not you knew that. How much a material costs is a property, right? If you have two reasonably identical materials, right, and one is cheaper than the other, guess which one is going to get picked a lot of the time? The cheaper one, right? Just simply as a cost property, right? The material now that you use for a particular design requires a set or a profile, as Ashby would call them, a set or profile of these properties. We want high strength typically, we want low density, we want low cost, right? We have all of these properties and we're going to pick, good and bad, or good from bad. Ideally all good with no bad properties, ideally. So material selection, you might think of it simply as identify the required property set, right? What are the set of properties that you require, right? For a particular application, you're not going to care about all of them, right? What are the properties you need for a water bottle, right? Okay, it has to hold liquid. So it has to be liquid tight. This one we're going to have to manufacture by blow forming. So hopefully it's probably a thermoplastic, right? Otherwise, you have to look at glass, right? So, you've got glass and plastic. We picked plastic for cost, perhaps. It has to be thermoplastic, right? So there's going to be certain requirements you have for an application, right? So figure out that set of properties you want, and then compare the set, right? Compare your list of properties with real materials, right? So you come up with a list of what you want for an application, and then you have to go find it. You have to compare it with real materials, because what you think of as your required properties, it may not exist, all of them in one material, right? So you look for the best match. Oh joy, focus, focus. All right, so properties here. All right, this is from that Ashby book, Material Selection in Mechanical Design. All right, so when you see these figures, it's from his book. So there are books. There are books and catalogs and libraries, both physical and online, that have all of these properties, right, in various forms, right? It could be in tables, it could be in graphs, right? Sometimes this data is very complete for a particular material if it's well used, or it might be lacking, right? You could be missing particular properties for a material because perhaps that material is just not suited for that use. So no one bothered measuring the properties. It's expensive to do. Or it's a new material that no one's gotten around to examining yet. All right. This is how Ashby classifies things in his book, right? He's got the materials universe. He's got the families of materials. So I said, we have ceramics, and polymers, and metals. All right, and those are your three main families. Well, again, that's not a law, right? That's just a general, rule that we think of. You could split those families up into slightly finer designations, right? Like ceramics and glasses, right? Elastomers, right? So you have plastics and elastomers, right? Structural polymers and stretchy polymers. Metals, hybrids, like a composite, right? And then under that, he has class, different metal alloys. Subclass, so, the numerical designation, which is well known by metallurgists, right? Individual members of the 6000 series. And then what Ashby calls attributes, right? So everything we know about aluminum 6061, a very popular aluminum alloy to apply. So it would have a very complete property set. We would know a lot of the properties of 6061, but maybe 6013 is less popular, so it's not as well known. It's not as well characterized, right? So it might be missing a few of the properties, maybe some of the thermal properties, or just no one ever measured them, right? So they're very hard to find. All right. So we've got all these, we've got ways of classifying them, and we document all of the properties, all right, somewhere, right? It might also be in the company you work for. You have your own private library of material properties, and that is also a thing. And so, if one company has those records, they don't share them with anybody, right? They keep those private, right? So there's public and private records as well. All right. So now, I started with this, right? Figure out the properties you require, compare it to all of the materials to figure it out. Well, it's a little more complicated. Right? It's a little more complicated than just comparing the requirements, right, with known materials. Because some of your requirements, some of your your design requirements are going to be more important, right? Not every property, not every requirement is equally important, right? This has to hold liquid. Does it matter if it's transparent or opaque? Not as important as it holding water. If this leaked, it would be a terrible bottle, right? So this has to hold liquid. What color it is secondary. That's not as important as it holding liquid. All right. Some things are more important than others. All right. So Ashby has this, right? A slightly more complex, right? He has a strategy, right? Or you might call it an algorithm. Perhaps you have an algorithm for how you do something, especially in computers. We have all materials. Translate design requirements, expressed as function, constraints, objectives, and free variables, right? First, you have to translate what the heck is he talking about, right? It's common in some books that the author comes up with their own vocabulary, which is not going to be known to anyone who's never read the book. So we have to figure out, what is he talking about here, for starters, right? Function, what is the component? What is it supposed to do? All right, it holds water. Constraints, what non-negotiable conditions must be met? What negotiable but desirable conditions must be met, right? This has to hold liquid, and it has to cost 1 baht per bottle, right, to manufacture. It'd be nice if it was transparent, but that's not a requirement, right? So things like that, and come up with constraints or boundaries, right? Objective, what has to be maximized or minimized, right? For this to hold liquid, right, it can't be porous. We'd want to minimize porosity, for example, right? If this was porous and it dripped, that's no good. We want to minimize porosity, right? We have something to minimize or maximize, perhaps. And free variables, what parameters can we change freely? And it's not really going to do much, right? So then he goes through screen using constraints, right? Eliminate materials that can't do the job. We're not going to make this out of ceramic, too expensive. We're not going to make this out of metal because, again, too expensive, perhaps. We're not going to make this out of rubber because it would just flop around, right? So we have things that would eliminate, right? We're not going to make this out of a sponge because it would be porous, too porous. Rank using objectives, right? Seek documentation, right? So you can get a little more in depth, right? You have all of these requirements. Some are very important and non-negotiable. Some of them you don't care about, quite frankly. All right. So the ones that are important, you figure out what you're trying to maximize or minimize, right? And then you can rank based on those properties. You can look at all the materials, eliminate the ones that are obviously never going to work, and then start to, it's called down selecting. You down select some candidates. Maybe you pick a dozen. Maybe you already know what you want to make it out of, right? But you pick some candidates perhaps, right? Then you look for documentation, right? You get everything. You get everything. All right. Eventually you have to make a decision. Now, to help you with this, because right now it just sounds like a lot of vocabulary, right? Can we just use math? Can we use math to help us? Right? Well, yeah, of course. Right? It may not be obvious how you put math to it, but if you think about it, eventually you can think of something. Right? There's probably examples like this. Right? This is a very, very old-fashioned plane. All right? But these still fly. These still exist. People make them sometimes. People have to repair them. Right? So we'd have different requirements for the different components on this. It's called a biplane. It's got an upper and a lower wing. So two wings, so a biplane. All right. We have things like columns, right, and little tie rods here and stuff like that, and beams. A tie rod, right, a tie rod here, which is pulling these two wings together to help stiffen the structure. It should be mechanically strong, and like everything on a plane like this, it should be light. So we want something that is strong and light. And then we look at constraints of this. What are constraints? Well, the length is constrained, right? It has to go from here, from there to there. It's a fixed length, right? Which is a kind of an obvious constraint in this case for design. It has to fit in a certain area. So the length is constrained. The cross-sectional area A, though, is not, right? It has to be a certain length, but the diameter, right? We could increase that or decrease that. Obviously, we're not going to make it a meter in diameter, and we're not going to make it a millimeter, right? So we still might have physical constraints, but it's pretty broad where we could fit that into. All right. Cross-sectional area is not constrained largely, and the material is not, right? We have free range to pick whatever material, right? Now, the mass. What is the mass of the tie rod? Okay, it's a cylinder, right? It's a cylinder, so it's simple geometry. We know that density is mass divided by volume, right? So mass is volume times density. What's the volume of a cylinder, right? Well, the height or length times the cross-sectional area. If it was circular, it'd be pi r squared, right? So the mass is AL not P, rho, right? And the area, the cross-sectional area, should be great enough to keep the stress below the failure strength, or perhaps the yield strength. You'd have to decide, is it okay if it yields a little bit? Or do I just not want it to break into two pieces, right? So you could pick various important strengths. Now here, it's probably going to be yield strength, right? You don't really want this to plastically deform, perhaps. Right? So you start to write these things down, right, to keep track of all this. All right, what's our function here? Well, it's a tie rod. It's a tie rod and a biplane to tie together two wings. Constraints. The length is specified, right? It's a geometric constraint. Tie must support axial load F without failing. So a functional constraint, right? It has to be this length and it can't break in half. Objective. Minimize the mass, right? We could do that with material density and cross-sectional area. If we make that smaller, right, it would have a less volume. So variables here, choice of material or cross-sectional area A, right? Look at the problem, you start to think, you write things down, and you figure out what you can change, what's a variable, and what you can't change. So again, putting math to this. Mass was cross-sectional area, length times density. So we can rearrange that to cross-sectional area, right? We're trying to keep the stress below some failure point, right? So force divided by area, right? Area was this term here, right? So we can put this term in here, right? So now we have this, the force times the length times the density divided by the mass, right? It has to be less than this specified failure strength, right? So we can rearrange it. Where we now have mass, right? And we have force times length times density divided by this strength term, right? So here's our functional constraint, here's our geometric constraint, and here are the material properties. So Ashby is separating the variables into different categories, And now he's got a material property thing here, density divided by a strength term. Right? So the mass of the tie rod depends on the force, which is constrained, the length, which is constrained, and two material properties, density and a strength term. All right? The ratio of density to this strength term should be minimized. Right? We'd want to minimize that term, density divided by a yield strength or a failure strength. Or if it was flipped over, you'd maximize it, right? This is to keep the mass low while still meeting the strength requirement, right? So we'd find that we want to minimize this term, which means we'd have a material with a very low density and a very high strength, right? That's how you get that less than 1, right? Very low density divided by very high strength. We wouldn't want high density and low strength. That would be stupid. We wouldn't use lead. That'd be a very poor choice. Some of this, it becomes obvious after a while, right? But here we can show mathematically why it's obvious, right? Because we want to minimize this term. So low density, high strength. And so now you find property charts. And this is what Ashby's books are known for, are all of these strange looking graphs or property charts. So here's a strength density property chart. Obviously, it's going to be common. It's going to be common in mechanical applications to want materials with low density and high strength, right? We very rarely want the opposite of that in a mechanical application. And you see all these materials, right? All of these different colored areas are encasing different families of materials. And you see down here foam. Foam has very low density, it's practically air, but it also has very low strength, right? And you go up here, metals. Metals typically have very high density and very high strength, right? So you can take these two material properties of density and strength and compare them against the different materials on a property chart, right? Boundaries can be set to limit the search area, right? So maybe we don't want a density greater than 3,000, right? And so we could draw a line, right? And we don't want a strength lower than 100 MPa, right? And so we would be looking in this region, right? And we see there are some metals in here, right? We see magnesium alloys. We see aluminum is very close, right? We see that there are ceramics perhaps, but as a tie rod, no, right? Perhaps a polymer, probably not. Well, maybe composites could be of interest too, right? So you see things like magnesium and aluminum, perhaps a composite might satisfy the requirements. We'd also have to consider perhaps toughness, right? And then cost and things like that. You see there's also different sloped lines here, which can also be useful, all right? So there are these. There's this idea that comes out of that ratio of two different properties. The ratio here, of strength to density or vice versa, is an example of what's called a material index, M, or what some people also call a figure of merit. My old boss used to like that term, figure of merit. All right. Many other material indices exist for a variety of design problems, right? The tie rod is nothing unique, right? They're also used in bridges, right? You can find tie rods in bridges and walkways and things like that, right? Not just airplanes, right? So this is not a unique design problem, right? So there are all of these different material indices for a variety of design problems, right? Once again, relying on material property charts to help aid in the material search, right? So, you know, tie rods, beams, right? Columns, right? So you might have a column in a bridge, right? Minimum cost, buckling load, right? Springs, thermal insulation, right? Electromagnetic, right? So all kinds of different indices with corresponding property charts. So an example, another example here. All right. A telescope mirror. Obviously, telescopes in Bangkok are not terribly useful, but if you get outside where it's dark, maybe you want one. All right, so there's different ways to make a telescope, right? There's different designs of telescope, just like there's different designs of bridges, right? Older designs for reflecting telescopes, right? So there are telescopes where the light comes in, and it hits a mirror on the back, and all of that light is reflected. It's reflected to a mirror here, which you can then see, right? So a Newtonian telescope. So there's a big mirror. There's a big mirror on the back, right? Big mirror on the back. Newtonian, it's Newton. Newton created this telescope years ago, centuries ago. So older designs for reflecting telescopes used mirrors made of very large single pieces of a material, right? Historically glass, right? So you have this big piece of glass up to 6 meters in diameter and 1 meter thick, with a weight perhaps approaching 70,000 kilograms, right? That's a big piece of glass, right? A large diameter allows for a telescope to gather more light, and so you get better performance, right? The bigger the telescope, the better the performance you get out of it. All right, doesn't matter if it's this big or 6 meters big. Bigger's better with telescopes, these optical telescopes. The problem, though, right, historically is, why don't we make them 10 meters or 20 meters or 30 meters? Right? Why don't we just make them as big as possible? Well, the mirrors in these things got so large that their own weight became a problem, right? Because they would sag, right? You'd get deflection, right? You get deflection delta here. And that creates optical distortion. This mirror has a particular curvature, right? So it can focus the light back to the eyepiece. But if it's so heavy that it sags down over time, perhaps, it's going to go out of focus, right? And you're going to get optical distortion, and you won't take nice, clean pictures. So you needed, a big support structure behind it to help hold the thing up. And so these things got bigger and bigger and heavier, and at some point it's just too much, right? So you have here, right, a big piece of glass fixed here on two ends, right, or in a ring. It has some thickness T, it has some diameter or radius, and perhaps some deflection. Right? Maybe we can have some deflection, but perhaps there's a limit, and if we exceed that, it's no good. All right. So for an improved telescope mirror, maybe we want to rethink this a bit. We'd want to minimize the mass, right? We like these things to be as big as possible, but we don't want it to be very heavy, right? We don't want it to be too heavy. So we don't want excessive deflection delta, right? Now here we know the wavelength of light, right? We know the wavelength of visible light goes from about 350 to about 750 nanometers. So we don't want it to deflect more than 350, right? We can have some deflection, but only a couple hundred nanometers, because beyond that, it's going to influence the visible focus. All right. So a large mirror radius is still desirable. So to minimize the mass, right, we either have to, decrease the thickness T, or perhaps find something with a lower density, right? So again, we have mirror mass here, right? Mass pi r squared T rho, right? So again, area and height or thickness, so it's a cylinder again, in density. So we have the mass, just like before. Mirror deflection. What's this deflection, right? You'll have other classes, I assume, where you'll go into beam deflection and stuff. But based on what is the shape of what's deflecting, you have different equations. So for a cylinder here, 3/4 pi here, mg r squared et cubed. And so you have modulus, you have gravity, radius, thickness, mass. All right. So again, we can rearrange things, and we get mass, we have gravity, we have deflection, we have pi over e to the 1/3. Right? So here's our material index, modulus divided by density. Right? The material index shows that a high Young's modulus, right, with a low density is desirable. So to keep the deflection low, we either have to minimize the mass, which perhaps we can do with low density, or we have to maximize, right? We have to keep the material very, very stiff. And we could also play with right? We could play with thickness, right? But that's going to impact the deflection as well, right? Yeah, it's going to lower the mass, but it's going to impact the deflection. So we'd have to figure out, does the thickness decrease the mass more or increase the deflection more? We'd have to think about that. So we'd go, okay, what's our function? A precision mirror, right? We want good focus with no deflection. Constraints, we're going to specify the radius, right? Maybe it's 3 or 4 meters. It's going to be big. Must not distort more than a couple hundred nanometers under its own weight. There are other properties as well, which you might have to consider, which wasn't obvious here, right? Creep, no creep, low thermal expansion, right? Thermal expansion. The mirror gets hot, the mirror gets cold, right? If it's changing dimension, again, it might be changing the curvature and the focus goes out of whack, right? So typically you want basically zero thermal expansion. You don't want any influence of temperature, right? A lot of telescopes go on top of mountains above the cloud line. It's very, very cold. But then perhaps the sun comes out during the day and it gets very, very hot. You don't want this thing expanding and contracting and changing the focus. Right? So basically very little thermal expansion. Creep behavior. Right? In some polycrystalline materials, over time, the material can sag. Right? You can get grain boundary sliding perhaps, where the material, it just sags under its own weight. Right? It's not just simple elastic deflection. It's more of a plastic deformation, a time-dependent plastic deformation. So you wouldn't want any creep either, because again, the mirror, it might change its shape over several years. And that would be no good. So we're trying to minimize the mass. To do that, right, we can play with the mirror thickness T, and we can play with the material. Ideally high modulus, low density. So again, we have a property chart, right? Young's modulus and density. right? So we had that indice here, e to the 1/3 divided by rho. And so there's a line here. There's a line here for that, right? And on this side, it would be bad. On this side, it would be good, right? That would be an example of that, right? So we have these sloped lines they're illustrating. We could move that sloped line around, right? And on that side, it's no good. On that side, it's good, right? So these are guidelines. Ruler and match the slope and slide it around, right? And again, you could set particular constraints, right? I want a modulus of greater than 100, right? And you see here, there are, what do we have here? Ceramics, right? Perhaps a composite's in here somewhere. Doubtful we're going to find a metal in this, right? But perhaps something like aluminum or magnesium again, right? And so it shows us we can eliminate things right away, right? Like a whole bunch of foam and elastomers and polymers. They don't have the modulus. They're low density, but the modulus is much too low. And so you consider things like some ceramics, perhaps some composites, maybe an odd metal, right? So we'd pick out several options perhaps, right? So in addition to the high modulus and low density, the thermal expansion should be small and it should be non-absorbent, right? It shouldn't soak up water. Telescopes are open to the air sometimes, right? You open a door and you look into the sky. Well, what if it rains, right? And it gets wet. You don't want it to soak up water. That would be terrible. Start to mold or something even. So we look here. Okay, steel. Steel is way too heavy. That's silly. But a lot of people think of steel for everything. Like, okay, can we make it out of steel? Because it's easy to work with and it's cheap. Well, steel is way too heavy and it would rust. All right. Graphite fiber reinforced polymer, not dimensionally stable enough, right? Thermal expansion and things like that. Aluminum alloys. It's a little heavier than glass, which is the original material, and it has too much of a thermal expansion. Metals, their thermal expansions are just too high for big telescope mirrors. For little ones, you can get away with it perhaps, for little toy ones, right? Newton's original telescope was made with a metal mirror in the back. Glass is the typical choice, all right, the present choice. Magnesium alloys, lighter, but you still have too much of a thermal expansion, no good. Carbon fiber reinforced polymers, incredibly light, not dimensionally stable enough. Right, again, the thermal expansion and the anisotropic properties of it's not going to be good enough. You see here it mentions radio telescopes. It might be good enough for other frequencies, other wavelengths, where perhaps distortion of it isn't going to affect focus, right? Our distortion is based on a couple hundred nanometers. What if you can have a couple millimeters? Then it's fine, probably, right? Foam polystyrene, very light, but again, it's not. It's going to be porous, and expansion is not that great. Plus, it's flammable. All right. There's no material. There's no material that we have outside of glass which would prove better for the gigantic reflecting telescope mirrors. All right. There's nothing better than glass that we can find. A new design, such as a segmented mirror, which is what people make now, especially in space-based telescopes. You don't make a gigantic mirror, you make a bunch of little mirrors and you put them all together, right? Kind of like a bug's eye. A new design would be a better choice. until a better material comes along. All right. So sometimes you have a design requirement where you just can't find a material that's going to satisfy it. So you have to change your design, right? Lower your expectations perhaps, or hope for a better material. All right. Which leads to the second half here. The idea of materials by design, or a better material comes along, right? These property charts, these have existed. These have existed for decades. And they didn't always look as complete as they perhaps do today. The early ones were pretty empty. They were pretty sparse. Material property charts have grown. They've grown through history, right? We slowly add to these charts, right? We add new material classes or new materials, right? Go back 1,000 years, we didn't have, fancy composites. We didn't have engineered ceramics or metal alloys. We had wood and we had rocks, right? So we had a very limited chart, right? Here, 50,000 BC, okay, gold, wood, leather, bone, shell, rocks, right? Thousands of years ago, it was a very simple chart. But modern day, these things they're jam-packed with different materials, right? But it can be a long wait for new materials to appear, right? So we might have this fancy design that we want to make, and we can't find a material for it, but one comes along maybe 30 years later, right? And by then, maybe your design was already superseded by something else, right? So waiting for a material is usually not a great idea, right? Because a lot of them, they're happy accidents. We discover a lot of materials accidentally, right? Somebody makes a happy accident and go, that might be useful. Like glass ceramics. They were a happy accident in 1959, right? We were kind of aware of them, but no one knew of their significance until one guy accidentally dropped it and it didn't break, right? So that's a bad idea, waiting for materials to just drop in your lap accidentally, all right? The wait could be very, very long, all right? So the materials by design approach now is the design of new materials. Rather than waiting for someone else to discover a material, can we go out and design it ourselves? Now, this is obviously getting into the domain of materials science and engineering. This isn't what every engineer is going to do. You're not going to run out and design your own material, right? Because this requires a lot of materials science knowledge, right? But you should be aware of this stuff. This is what some materials people do, right? So materials by design, MBD. It's the design of new materials at various length scales. So from nanometer to meter, right? There's different scales of a material. We can design on all of those scales, perhaps. So from the atomic to the macroscopic, in order to generate new or improved mechanisms or properties for a particular application, right? So can we design how a material functions to give us a better property, right? This is a little bit opposite to the Ashby approach of material selection from existing property charts, all right? Ashby, we have these materials, they exist commercially perhaps, we pick the one we want or the closest best thing, and we go with that. This says, let's just design exactly what we want and make that, all right? This gets into like materials philosophy, if there is such a thing, all right? So this is from Macaulay, engineered ceramics. This is my old boss at the Army. who was arguing for this for decades. All right. So, same idea, right? System performance requirements and functions. What is it supposed to do, right? What you'd normally do is you go through material selection, right? And this is the Asht approach. So we want to build a water bottle or a phone or body armor in the case of the Army. And we decide on the requirements we want, and we try to pick the best material. That's the Asht approach. Ideas of property charts. And we might find that the material just doesn't exist. The requirements that we want, they're too up there. There's no material for that. But if we really, really want that performance, we might do materials by design, where we're going to design or invent an entirely new material, right? You know, or perhaps try to optimize stuff that exists already, right? So there are different approaches, right? We find the best material that exists. Doesn't exist, we'll invent one. Well, maybe we can just optimize one that we have. Maybe it's close and we can make it a little better, right? So there's different ways you can go about these things, right? Especially with computers now. You can start to imagine you can use computers to help optimize materials, perhaps. Right? So here's an example with a radome. A radome. The word radome is a contraction of two words, radar and dome. A radar dome, a radome. It's a covering for a radar antenna, right? Found on ground-based radar systems, in spacecraft, in aircraft, in boats, in cars and trucks, and missiles, right? Its job is to keep the antenna protected from the environment, right? So there's this radar antenna, and it's pointing out, right? It's outside, and we want to protect it, right? From things like wind or rain or hail or dust or erosion or birds or who knows what, right? So examples. So this looks like an F-15 or an F-16. The nose, right? Fighter jets, they have these pointy noses on the front, right? They're there for two purposes. One is it's aerodynamic, right? Because these things fly very, very fast. And two, it's protecting the radar assembly inside the nose, right? So you see this nose, it opens up. You can open up the nose on these things. Who's that? Mute. Mute. Going. So these things open up. They provide aerodynamics, and they provide protection for this thingy. That's the radar antenna. So the nose cone here is an example of a radome, right? A missile, it's the same idea. This pointy thing, the front of the missile, it's there for aerodynamics, and it's there to protect the guidance system, right? It's there to protect the guidance system, the little thing steering the missile towards the target, all right? So it's aerodynamic, and it's mechanically protective of the antenna behind it. Right, so that's a radome. So a radome, it needs to be mechanically strong, all right? It needs to have an aerodynamic design that's separate from this, and it needs to be transparent to certain frequencies of electromagnetic radiation, right? This isn't visible transparency, right? It's not looking through a water bottle, not visible transparency, but perhaps infrared transparency or microwave or radio, whatever the radar antenna is based on. It needs to be transparent so the antenna can see through it, so it can get signal. It wouldn't be a good radome if it reflected all of the energy, right? That wouldn't be good at all. So it needs a different spectrum of transparency and mechanical properties. All right? The required strength will depend on the applied stress or delta P. It's some pressure differential. Typically as a function of speed, if you're on something moving, obviously. It'd be a static load if it was on the ground. So you might see something like this here, right? Function, okay, it's a radome. All right, a radome is this thing here, this dome, protecting this radar antenna. Here it has a particular size, a particular thickness, and there's some pressure, right? Some pressure. So support a pressure difference delta P, tolerate perhaps some temperature gradient. What are we trying to do? All right, meet those strength requirements and minimize dielectric loss in transmission here, say microwaves. It's a microwave antenna. What can we change? All right, thickness and material selection again. All right, transparency. This will be minimum dielectric loss. Minimum dielectric loss. Right, this is not visible transparency. So we have minimum dielectric loss. This will depend on the dielectric constant, right? So you might see dielectric constant K or perhaps epsilon. This is basically reflection, right? How much is it going to reflect from the material? And the electric loss tangent or tan delta here, which is basically the absorption component. So it's the same ideas, right? With visible transmission, you had reflection from the surfaces and you have some absorption, right? Now we're out of the visible, right? But we still have ideas of reflection and absorption here depending on dielectric constant and this tan delta, all right? So these would be the electrical properties. The electrical properties of the material impacting the electromagnetic transparency. Right, so again, seemingly dissimilar properties together sometimes. And here we've got mechanical and electrical all of a sudden. Right? So we might see these things getting into these material indices. So fractional power loss, right? This depends on the frequency and the amplitude and the thickness, the dielectric constant, and the loss tangent, tan delta here, right? And the strength, right? And so we could try to put all of this math together and we get this. We get this as a material index. Some fracture strength or failure strength. And here, we had dielectric constant and tan delta, right? Trying to minimize the power loss. Right, so we're combining things which most people wouldn't ever think of putting together for everyday use, right? The material needs to be thick enough. It needs to be thick enough for the strength, but thin enough for high transmissivity, right? So we're trying to balance the thickness here. Thick enough for strength, thin enough for transmissivity, right? So we can play with thickness and we can play with material selection. So the material index M, or figure of merit for a radome, right? A mechanical strength divided by the electrical properties here. All right. So here, epsilon is dielectric constant, or K, and tan delta is the loss tangent. And again, you can plot this. You can plot this on an Ashby plot. So here's strength and dielectric loss. You go, that's a weird graph to see. And you look here, all right, we're trying to minimize this stuff. We want this to go that way, and we want that to go that way. And when you do that, there's nothing there. There's nothing there, right? So you have to tolerate that you're going to have some loss, or you have to have a lower strength. Now, maybe you can tolerate loss if you can turn up the amplitude of this thing. You could just boost the signal. Maybe you could tolerate that loss. Or maybe you can tolerate lower strength if you go slower. Things like that, right? But you look here, right? High strength and minimum losses you're getting here. You see engineered ceramics, right? You don't see metals pop up on here because metals are not going to be transparent to these frequencies, to these wavelengths. They're not transparent, they're reflective. So this only has sensible materials which might work. It doesn't have ones which are going to be impossible, like a lot of metals. So you see engineered ceramics, right? You see silica over here at low loss and relatively high strength. And you see perhaps some composites, right? Some composites are perhaps lower strength. So maybe we've got new ones since then. And again, you have a design guidelines. You can take this on a ruler and move it around and help eliminate things that way. All right, so you look here. And ceramics, they tend to be used a lot for these applications. All right, for things like missiles, right? On an aircraft, you're probably not making that out of a ceramic though. So maybe composites come back into the mix. Glass is a candidate if you're trying to keep the cost low, right? So glass would be in here. So you see soda glass. Glasses would be a candidate for low cost, right? Fused silica, or perhaps some engineered ceramics, right? On something like a missile, this is one-time use, right? You're going to make it and break it. On the aircraft, it's going to have to last for a long time. So here, maybe you spend the money. On the missile, maybe you're trying to minimize cost. Now, if we needed even higher strength and lower dielectric loss, right? There's nothing here. What if we're trying to be down? What if we're trying to get into this box here? There's nothing there, right? There's nothing between 10 to the minus 5 and 10 to the minus 4 with a strength of a gigapascal. It's not there, right? Some of these are close, right? We could perhaps optimize it, or we could think about materials by design, right? There's no material if we wanted to go to the extremes. So a new material would likely need to be designed, right? And looking at the closest regions, it's likely some kind of ceramic or possibly a composite, right? They are the closest regions, and you know, these regions can be pushed out. We can expand the front, right? We can try to expand the front. So we'd have to figure out how these things are working. What are the mechanisms, right? What are the mechanisms at all the length scales to explain why these things have a particular strength, or what impacts that dielectric loss? We'd have to understand that to figure out how to make a better material, you know, to expand the front or to completely jump to a new area, right? And see a quote like this. Characterization describes those features of the composition and structure, including defects, of a material, right, that are significant for a particular preparation, study of properties, or use, and suffice for reproduction of the material. This is Rustum Roy. He's a famous ceramics professor from Penn State. So, with these charts, right, materials, they encompass an area. We can try to expand the area, or we can just jump to a new area entirely and invent one. But to do that, you need an awful lot of characterization. You need to know how things are functioning so that you can try to make them function better. All right. So we saw that something like fused silica here is pretty close to where we might want to go, right? Maybe we want to lower the loss. Maybe we want to lower the loss because it's strong enough, but it's a little lossy. What's impacting transmission? What's impacting the transmission through silica? Right, and this would be an example for visible light, right? Because I had this. Right. So we look at the transmission curve. The transmission curve for fused silica. So here's percent transmission, 0 to 100, as a function of wavelength or frequency. Right. Fused silica. This is just silica glass. So take a bunch of sand and melt it into glass, and you'd have something like fused silica. And you'd see in the visible region, there's very high transmission, right? And then we see that it decreases as you go towards ultraviolet and infrared, right? So maybe we wanted infrared transmission, right? For, a heat sensor, a heat detecting missile or something like that. We want to see IR. And we see that it falls. There's an edge. There's an edge on both sides. It's a plateau, all right? The UV edge, the ultraviolet edge for fused silica. Why does it go? Why does it fall? It's due to electronic transitions, right? Electron excitation in oxygen, right? Remember, electromagnetic radiation is energy, and that energy can interact with the material, right? In visible light, right? The photons can polarize the electrons, right? And they slow down in the material. If it's sufficient, the electron can absorb the photon and become excited, right? And so we find when we get to the ultraviolet side, that's what happens. The electrons absorb all of that energy. They become excited. And it's from the oxygen, and it's from the anion in the glass, right? The exact location here depending on the stoichiometry, the chemistry. And so this can move around. Infrared is a result of bond vibration. Remember, atoms are always moving. And because they're bonded, right, those bonds, they vibrate. And they have different modes of vibration, right? If you take chemistry, you may have heard that mentioned before. Bonds have different vibrational modes. Right? They can stretch and bend and twist and things like that. And so the IR edge here is a result of that bond vibration. Right? Again, it might depend on stoichiometry. And we can have things like absorption bands because of things like impurities, like water in the glass. Right? So electron excitation, bond vibration, that's impacting transmission through our material. Right. Now, what if we looked at a different glass, like a soda lime silica glass, window glass? But I said, maybe you want to make a cheap missile, and you look at, well, I'll use ordinary glass. That'll be really cheap for a radome. And when you do that, you create defects. You create defects in the glass network. And it does exactly the opposite of what you want it to do, right? When we add alkali, we create non-bridging oxygens, and that moves those edges the wrong way. We go the wrong way, and we'd make our radome worse. It would have more loss, perhaps. All right. It's decreasing the energy to excite the electron in oxygen, right? It also shifts the absorption bands in the IR, right? So we go, okay, what is it depending on? Right, okay, we made it easier to excite electrons in oxygen by adding these defects. What about IR absorption? How does it affect bond vibration? Right? Well, that might depend on things like mass, atomic mass, perhaps. Right? So these are different vibrational modes, right? Different types of vibrational modes you can get. Right? Different non-bridging oxygens create new vibrational modes, which might negatively impact the properties, right? These are examples. So this would be a silicon oxygen tetrahedron. And these things can be expanding, they can be breathing, right? So expansion and contraction. You have these degenerate weird modes here. So we'd want math. We'd want math to look at this. You know, the vibrational frequency, right? The vibrational frequency here, it's depending. It's depending on the mass of the atoms. The mass of the atoms. So do we have two light atoms or two heavy atoms? Or one heavy and one light? And the force constant, it's basically the bond strength, the spring strength. Is it a really stiff spring or is it a really weak, soft spring? That's going to impact the vibrational frequencies, right? So see the absorption edge, it shifts towards the IR. So if we wanted a heat-seeking missile, we want to shift the edge into the IR, so it's not absorbing IR. We want it to transmit IR. So we might find we have large elements with weak bonds between them. That would perhaps shift it into infrared. So we don't want to use our silica. We want something that's heavier and weakly bonded, more ionically bonded perhaps, and less covalently. And that would move the edge the good direction for us. So that's the kind of stuff you study. All right, and you see there's different glass chemistries. Right. Maybe we're pushing this out. Maybe these are chalcogenide glasses. Right? These could be chalcogenide glasses. They're not even visibly transparent, right? But IR, they're transparent. Right? So maybe we have new glass chemistries to expand that with. All right. Now, I'll mention this. Static versus dynamic applications. Now, civil engineering structures, for the most part, are going to be static, right? You build it and it stands there for decades, right? So you care an awful lot about static properties. But remember I mentioned with mechanical properties, there is the effective rate, how quickly you test a material. So if you design a car, you care about its behavior when it crashes into something going very quickly. All right. So you have static versus dynamic. And this is something that if you work in the Army, you might care an awful lot about dynamic properties of things like armor, right? A bullet going a kilometer a second hitting something, that's a very dynamic application. And so maybe you need to consider designing a material for different rates, right? Not just static, but dynamic events, a dynamic failure, right? So you can consider design with rate effect, right? So just some examples in this table here, right? A bend bar or a dog bone, like I showed you, right? We're testing maybe the tensile strength of a metal, right? That's quasi-static, right? Versus a dynamic event like a bullet hitting a target, right? Stressed volume. How much material are you testing in a tensile test? It's a very small volume, actually. In a dynamic event, you test or you load up an enormous volume of material simultaneously. So when you think about failure statically, you think like Griffith. You think it's the largest flaw, and the material fails that way. In a dynamic event, there's a whole lot of flaws, and they can fail simultaneously. Right? So it's not just the biggest one. There's a distribution. Right? Maybe it's the tail, the very, very largest defects, and there's more than one. Right? So statically, you have one crack. You break a dog bone, you get basically one failure surface. Dynamically, a lot of failure surfaces, right? Strain rates, 10 to the 6th. Here you're, 10 to the -2, quasi-static. Strain rates are enormously different. How are things failing, right? Okay, you get dislocation movement, right? Grain boundary slip, stuff like that. What happens dynamically? All kinds of things I never talked about because it's not relevant to static applications. But you might start to create things like stacking faults and amorphization, right? You could have phase transformation. I mentioned that. Things can actually melt if you hit them fast enough, right? So this is something you have to be aware of. What are the mechanisms? What causes something to happen? What causes a mechanical failure? What causes an absorption edge? Right? That's what we have to figure out. And we don't know them all, right? We discover new ones to characterize things. All right. Stress characteristics, gradual rise, all kinds of new things like shock waves, right? Compression waves, Hertzian cone cracks, spallation. Things can fail in very spectacular ways. Right? So it's an example here. Here's a ceramic. I broke this in bending. I broke it in bending. This is quasi-static, right? This is ordinary mechanical properties testing, quasi-statically. And this has all the features you expect from a quasi-static bend bar. A compression curl, right? And different crack features, right? And a failure zone that we could figure out the flaw, the one flaw that made it fail, right? We can zoom in and we find that the flaw is up in here, right? We see some interaction with the microstructure and we see some secondary defects, but we find a flaw, right, on the surface. This was a bend bar, right? And you push on it, right, in bending, and it's going to have a flaw. In this case, it was basically a crack on the surface, right, from a piece of graphite, which was used to manufacture it, right? So we could identify these flaws and help eliminate them and make stuff better, right? But then we could look at this dynamically, the same material. What if you shoot it with a bullet going 800 meters per second? You don't get 2 pieces, you get thousands of pieces. It doesn't just break in half like you drop your plate on the floor. It explodes basically, right? So you get thousands, tens of thousands of fragments, right? So this was shot right there. You get different types of cracks, and you could look at all the different fragment sizes. And then you could study that. You could study those fragments and find new mechanisms, right? This was somebody being curious and doing something as simple as counting the broken pieces and realizing that the broken pieces, there was a significant difference in the number of pieces when you went to a higher velocity. The number of pieces got dramatically different all of a sudden. And so somebody looked at that and they figured out that boron carbide goes from crystal to glass. It becomes amorphous at a particular transition pressure, which nobody knew about. This was back 2003, right? Statically, when you test materials, you may not initiate certain mechanisms. And you go faster and faster and faster, and you get new mechanisms which change how a material fails. And that's what this did. This picture you're looking at, this is 3 nanometers. You're seeing the planes of atoms. You're seeing the atomic planes of boron and carbon. When you see the planes, it's crystalline, right? Here, this B, this illustrates it's crystalline. This is a diffraction pattern that says crystal. This mush here, this is amorphous. The boron and carbon, now they're randomly arranged. It's glassy. A, this is also a diffraction pattern. This says it's amorphous. It's glassy. So this was a new mechanism, right? And you could zoom out. And so we look at a different scale. This is 20 microns. This is 20 microns. And we see this. We see this gunk, right? This gunk. And you do different characterization. You do Raman spectroscopy. Not ramen noodles, but Raman, the Indian scientist. And you look in here, and you look in here. This is amorphous, and this is graphitized, right? So different vibrational modes, right? So this is something we figured out. When was this? This was 2007. Wow, I'm old. All right, so with something like boron carbide, right? Boron carbide, you'd want to use it as armor, right? As ceramic armor. But it has limitations, right? It falls apart at particular pressures. And so you can't use it against certain things. It's just not acceptable. But we like it because it's light. It's got low density. We'd have to use other heavier materials which don't fall apart at certain pressures, right? So if we wanted to use boron carbide, if we want to push the boundary, we have to understand why it falls apart and then figure out how to make it not do that, how to change this mechanism or put in alternative mechanisms. And so you have to characterize. You characterize the heck out of the material, right? At different levels, right? You figure out what's going on, right? And you try to get all this information together and you stare at it, right? So things like crystallography. Remember those crystal systems? That stuff's still important, right? How do the atoms arrange in the crystals, right? How could we maybe control that, right? What happens when we smack it really hard and we get new mechanisms of failure? How do we fix that? How do we control it, right? That's all part of the process. And here's a comparison. So again, these are two different armor ceramics. Ceramics we use to stop a bullet. Boron carbide, silicon carbide. We like boron carbide. It's low density, lower than silicon carbide. But silicon carbide works better to higher pressure, which we also like. And you have to figure out why. Why does this one work better than this one? And so you can compare them, you characterize them, right? And you look at they crack differently in a macroscopic scale. They fail differently in a microstructural scale. They have different cracking, right? This one, it cracks around the crystals. This one, it turns them into powder. It pulverizes them. Shear localization. You can look atomically, right? This one turns to glass. This one creates twins, a type of line defect, right? So we look at all of these different scales and figure out how it works, and then try to figure out how do we design it better, right? How do you eliminate this, right? Does it have to do with the grain boundaries? Can we design better grain boundaries so we get better cracking? You know, that, and you research that for a few years to figure it out. All right. And so this leads to an idea like this, right? Again, I worked for a guy in the Army, and so this was lots of Army stuff. Protection materials by design, right? Do we have a figure of merit, right? Ashby has a figure of merit that we want to maximize or minimize a ratio. What's that ratio for body armor? Is there something like that? And so you got to think that direction now, right? Again, a whole bunch of detail, all right? And so in early one of the 1960s, maybe it's modulus and hardness and density. And maybe this will be our figure of merit. And so we only want ceramics with low density and high hardness and modulus. And that's where you get things like boron carbide and silicon carbide and alumina and titanium diboride. But this doesn't have anything dynamically. There's no dynamic, these are not dynamic properties, right? Armor works in a dynamic regime. And these are all static properties, right? So people in dynamic problems, they like to link to static, and that becomes an issue. Can you do that? And so people also research that, right? There's lots of different research fronts here, all right? So you could look at something like this now, all right? You can look at the stages of bullet armor interaction and go, what's happening here? What's happening here? Right? So you see here, velocity, right? There's all kinds of things that happen when you shoot a bullet at a piece of ceramic, right? There's lots of things that happen, which you can't see because it happens quickly. You can't see it with your eyes, but we can see it with cameras and x-rays, and we can slow it down and go back and study it. There are things like shock and dwell. Believe it or not, when you shoot a bullet at something, it doesn't just go whoop right through it, right? In something like a ceramic, it might actually whoop. It dwells on the surface temporarily. The back of the bullet's moving, but the front of the bullet is stopped on the ceramic. That's called dwell. Dwell is very important, actually. And eventually it will go through. It will break into the tile, right? And you'll bend the back plate, right? Maybe a figure of merit, a material index, should incorporate some of these things, some of these dynamic events, right? So Ashby's design problems are largely static. And so he has static figures of merit. But if you have a dynamic design problem, maybe you need a dynamic figure of merit. And you have to figure out how to do that because no one really has. Right? And you can see, the figure of merit, it might have to be very, very variable because dynamic events are incredibly variable, unfortunately. Right? There's a lot of words. I don't want to go through all of these. I'd rather talk about other stuff. All right. Now, something like hardness, right, might actually be useful as a dynamic property. Even though it's a static test, its failure, the failure in the material mimics, it kind of copies dynamic failure to some degree. And we've known that for a long time. And you try to study hardness as a substitute for a dynamic property. This is an example of a hardness load curve. Right? So on your phone, right? You scratch it, right? You get scratches in it from hard substances like sand and dirt in your pocket. And people talk about, you know, the hardness of your phone screen. They're really talking about scratch hardness. There's also indentation hardness, the resistance to penetration by something. All right. That hardness, it's a function of how hard you push. Right. When you have a very low load, so that's increasing that way, it's going that way. When you have a very low load, the hardness a material has looks very, very high. But as you increase the load, the hardness comes down. And so you see this hardness load curve or indentation size effect. And we know that here, we're looking at elastic. Here we're getting into plastic deformation. And this mimics dynamic behavior a little bit. And so people look at hardness for armor, right? And so you can try to plot. You can try to plot a lot of data. A lot of data. So these are different armor materials. This is the load. This is the new hardness. And you try to find something in here. Try to find that little nugget of gold. What's going to be useful, right? The inverse of this slope is a possible means of quantifying quasi-plasticity and the transition velocity. There's lots of events in a dynamic lots of events in a dynamic event. When you shoot a bullet, lots of things happen. One of those is dwell, right? And there's this transition velocity, right? At what velocity do you go from dwell to penetration, right? Maybe you could kind of predict that with a hardness test. Right? Hardness, you're pushing on it, and at some point you penetrate. It's like a bullet. You shoot it at a low velocity, it just bounces off. At a higher velocity, it goes through it. So it's kind of like hardness in that respect. And so someone tried to figure that out. Can I relate hardness performance to a dynamic thing like transition velocity, to dwell, right? You get a bunch of numbers and you make up a curve fit, right? And you try to predict it from hardness, right? And so you have measured transition velocity predicted, and you go, yeah, it's kind of close. It's not bad, right? All right. Summary. That last bit that's like kind of fairly recent armor ceramic research. Just to illustrate, all right, there is a whole lot about materials I haven't covered, I've never mentioned, I don't possibly have the time to cover in an introductory class. But be aware, there's a lot of really interesting and novel and exciting research. Exciting is a relative term, but right. It's not just, steel and cement and plastic and stuff like that. There's a lot of interesting materials which can possibly be used in designs if the cost is right. So summary here. Part of materials engineering is being properly select and apply materials to a design problem, right? Now, there's different types of civil engineers. Some of you will focus on design. Some of you will build things, right? Some of you are just going to survey stuff, right? But at some point, maybe you have a design and you have to figure out how to pick a material for that, all right? A common approach to that is based on the ideas of Ashby, Michael Ashby, with all of his books. Decide on a set of requirements for your design, right? How strong do you want it to be? Things like that. And using math and things like property charts, you pick the best existing material, right? And that's perfectly fine in something like civil engineering. Perfectly fine. If the best, it should be existing, not exiting, existing. If the best existing material is still not good enough, right? You have some entirely new design concept, or you have some very dynamic application like aerospace or armor. New materials can still be created. We haven't discovered all the materials there are. Right? We can make new ones all the time, and composites explodes that front. Right? So this is the idea of materials by design. Right? Sometimes the material's not good enough, and we want to make it better. All right? But to do that, that is the domain of material science and engineering. All right? You need an in-depth knowledge of how a material responds at all levels to different types of external stimuli and how you can change that, right? That's the fundamentals of material science and engineering. Understanding how it works, change it to make it better. All right, so that's the end of that. That is the end of the formal lectures. All right, now, there are a bunch of worksheets I want to go over, right? But I can't do all of them today. So I'm going to do, I think, half of them today. And again, like I said, I'm gonna have another meeting later in the week, like Thursday or Friday, and I'll have returned the rest of your worksheets by then, and I'll go over those worksheet solutions at that time. All right, so these are the ones I've returned. All right, and I'll mention the final at that point too. All right, so let me go over these. Now, with a lot of these worksheets, a lot of you, some of you do perfectly fine. And then a lot of you make the same mistakes because a lot of you all work with your friends, to put it politely. All right. So these are the solutions. Again, you can study these on your own, but I want to explain them. All right. Because there's more than just the answers in some of these slides. So this is that Hall-Petch problem. Right. So this is back just after the midterm. Right. Where it was found a long time ago that the yield strength of metal is often correlated with the grain size, right? So metals have crystals. Metals are made up of little tiny crystals, all smushed together, polycrystalline metals like steel, right, or aluminum. And it might be observed that if the metal has a very, very small grain size, very tiny crystals, it was stronger than a metal that had very, very big crystals, right? And so this was noticed by Hall and Petch. So it's Hall-Petch behavior. And it doesn't just happen in metals. It's observed in ceramics and polymers to some extent, though it's not just grain size at that point. Right, so the mechanical properties of materials can depend on grain size. And that depends on how you make the material, how you process it, right? So the Hall-Petch equation relates yield strength, sigma sub y, to the grain size, d. A, construct a graph, sigma sub y versus d to the minus 1/2, right? So MPa versus mm to the minus 1/2, using the data provided in the table. Label the axes, all right? Label vertical and horizontal. What are they? Determine the values of sigma naught and k sub y, right? So there's the Hall-Petch equation, right? We have yield strength and we have grain size, and we have these two parameters, sigma naught and k sub y. All right. Again, don't forget their units. What are the units of these things? Rearrange the Hall-Petch equation to solve for grain size D, and using the values of sigma naught and k sub y, calculate the grain size in microns if the yield strength sigma y is equal to 550. Right? So you have this data. It goes up to 400. You can use the equation to extrapolate. You could say, if I want 550 MPAs for yield strength, how small do I have to make the grain size? Right? You could use the data to extrapolate, to say, I want it stronger. How much smaller do I have to make the grains? 4 microns? 1 micron? Nanometers? What is it? Right? So you have data. And if you have math to describe the data, you can use it to extrapolate or interpolate sometimes, to ask what if questions. And so you have this. So here's your table. We have a graph. And like in the lecture slides, it was sigma sub y and d to the minus 1/2. Right? D to the minus, this is to help make this linear. Right? Itchy eye. So we need this. We have d, and we need d to the minus 1/2. All right. So here we have 1 over the square root of d. Right. Now, if this is millimeters to the minus 1/2, and this is microns, you should convert it to millimeters. All right, that would be typical. Like some of you did it in microns, and some of you did it okay, and some of you made mistakes because of that, because you started mixing and matching. All right. When you're first learning something, it's often best to just mimic, to copy exactly what the source is doing until you kind of understand that. And then you can start to play around and see how it changes if you alter something, right? Some of you jumped right into that and you didn't understand that you did it wrong and you got weird answers and you didn't know it, right? So it's often best when you're teaching yourself something to just mimic the source, right? And get comfortable with that and then try to change it, right? Once you understand it better, right? So you would do this to calculate d to the minus 1/2. And you see it came out to nice even numbers because I designed it that way. I didn't pick these randomly. I picked it so I got nice whole numbers here. So it's easy to graph, right? So we have 4, 8, and 14. So 4, 8, and 14. And we have our strength values. Those don't change. So 150, 250, 400. All right, 3 points. Now we have a line connecting them. All right, that would be our graph. And you could extrapolate these lines. You could extend these lines, right? If you extend it here and you cross the vertical axis, you're getting sigma naught. Right, you're getting sigma naught. Which if you look at this, you go, 0 grain size? That's how you might interpret that. That's not what it's supposed to mean. It's not actually 0 grain size. It has to do more with crystal slip. All right. That's why we don't like a lot of these naught terms in equations, because we don't always fully understand their significance. So we try to eliminate them. Right. But this is saying 0 grain size. Right. Or, some like weird giant grain size, right? Which isn't really the case. But here, you extend the line. You extend the line. And if you graphed this very well and you used a ruler to draw everything like you should, you would find it intersected it at 50, right? 0 and 250. So 200, 150, 100, 50. Right? So that's 50. 50 what? Well, it's on the the yield scale 50 MPa. All right. So at some enormous grain size or something, it's saying it's 50 MPa. All right. Now what's KY? KY is basically the slope of the line from the lecture I showed you. Slope is rise over run, if you forgot. Now, what's the rise? The rise is the yield stress scale, the yield strength scale. The run is d to the minus 1/2, mm to the minus 1/2. Now, you could just try to pick 2 points off of this and figure out the slope, or you could just be smart and use the data points. We have 2 data points. We don't have to make up our own points. So point 2, I picked 414, and point 1, 150 and 4, right? And you do the math, right? Rise, 400 minus 150, run, 14 minus 4, MPa divided by mm to the 1/2, or KY is 25, mm to the 1/2, right? This is minus 1/2 or positive 1/2, depending on where you put it, right? Depending on where you put it. So this would be a unit, or this would be a unit, all right? But again, if you left it blank, I probably took off a point. All right, so now we know everything in here. We know sigma naught, we know KY. If we wanted to find a grain size for a corresponding yield strength, we could just rearrange the equation, right? So D equals KY over yield strength minus sigma naught squared. Plug in the values. We want to know D at 550 MPa. In this case, we can leave this in MPa. We don't have to go 10 to the minus 10 to the 6th or something like that. You don't have to do that. So we have 25 divided by 550 minus 50 equals 0.0025 millimeters. This is in millimeters, right? And we get 2.5 microns. Right? This is going to be a weird equation, right? Pascals, newtons per meter squared, and we've got millimeters here, right? So if you start playing with different units and you don't understand what's going to happen, you're going to get weird values, and you're not going to know it, right? So to get 550 MPa, we would estimate 2.5 microns should be the grain size. All right. Now, how do you double check this stuff? Right? I've always hammered on that with other problems, is how do you double check things, right? And stuff like that. With your graph, if you left enough room, you could extrapolate it. Right, we want to find 550. There's 500. There's 550. Boom, right there. I left just enough room. This would correspond to d to the minus 1/2 of 20, or d of 2.5 microns. Right. Now you can just use the data directly. Graphing is so we can visualize something better. Right. We can see that this is a linear relationship, this equation, right? It just helps us visualize what's happening. You don't always have to use a graph, right? I had you draw a graph just because it's good practice, because sometimes you have to make a graph and you have to label it and stuff like that, so it's complete. But you can just manipulate the data too, right? You don't always need a graph, right? So again, KY, right? Just take 2 data points. We know it's linear, it should be linear, right? We can just get it directly from the data, right? We can then directly calculate. We can calculate sigma naught. Again, we know KY. We can pick a data pair and solve for sigma naught, right? We get 50 MPa. And again, we know the equation, we can manipulate the equation, We can solve for different variables, and we can directly solve for D, right? So if you have data, if you have math describing the data, you can manipulate the data to extrapolate or interpolate, to make predictions, right? Or to figure out data points that you didn't know, right? All right. That was worksheet 6. All right, worksheet 7. Still going here, because I got some time. Glass batching. Glass batching. All right, so I gave you this problem. Again, so glass batching, you're probably never going to be glass engineers. But this is similar logic to how you might batch together other materials like concrete or cement, right? You have some recipe, and you have some math that you can use to manipulate the recipe to make it bigger or make it smaller, or to account for things which might lose or gain material, right? So you have the same thought process in other materials, right? Polymers, they do similar things. Metals, they do similar things, right? We want to make something, we have this math to follow so we can make it, account. Right, so this is for glass. Calculate the weights of the 4 oxide powders necessary to make 3.3 kilograms of glass with the following molecular formula, right? Recipes come in different units, right? And you have to know how to manipulate those units to transform it to something you might understand better. Glass, a lot of the recipes come as molecular formulas, molar formulas, which is unfortunate because we don't have a balance in the laboratory that works on moles, it works on grams or kilograms. And so we have to be able to manipulate a molar formula, right? This is like chemistry class. 12 moles of potassium oxide, 4 moles of alumina, 7 moles of boron oxide, 68 moles of silica. All right, so those are the pure oxides. Fill in the table to help you make the calculations. Right? A lot of this is done in a factory on software, right? Be it, are you batching concrete or cement? A lot of this is done with software. Somebody had to design it, right? Somebody had to know the math to put into the software. And you should also know it if you're going to use it. So sometimes you might buy really crappy software and they didn't make it right. So you can use a table to help keep this neat and organized. For glass, you might have a dozen different things, and it could get complicated. So you make it in a table. All right. So oxide powder, potassium, alumina, boron, silica, molar mass, grams per mole of this oxide. Molecular formula, mass formula, weight percent, weight fraction, the required batch amount, and what we would finally weigh out to batch this so we could melt it. All right. So I color coded this a little bit. So molecular formula, right? The number of moles. Potassium was 12, alumina was 4, boron 7, silica 68. Right, so you write those down. All right, corresponding to that. All right, so that's the molecular formula. This can add up to any old number. It doesn't have to add up to 100. It's not a mole percent. It's just a molecular formula. It's mole. It can be anything it wants to. All right. It doesn't have to be reduced to any set of numbers. It's anything. All right, it's not a mole percent or anything like that. Right? To calculate the mass formula, it's simple multiplication, right? This is grams per mole times moles and those cross out, and we're left with grams. Wait, what is this? Nonsense. All right. So multiply. All right. Use your calculator. Use Excel, something like that. All right. So we get 1,000, 400, 487, 485. Add those up. All right. 6,111.02 grams. All right. So that's the total. Now we want the weight percent and the weight fraction. All right. We're trying to normalize this. This is 6,000 grams. We want to normalize it to something so we could scale up or scale down, right? So you can normalize it to a weight percent or a weight fraction, to 100 or 1, all right? So weight percent, the component oxide mass, the mass formula, divided by the total mass, multiplied by 100. That will give you the weight percent. So for potassium oxide, it was 1,130 divided by 6,111 times 100. And you get 18.5%. This molar formula is 18.5 weight percent potassium. All right. And you do that for the rest. 6.67, 798, 6685. Whenever you do these things, metals, ceramics, concrete, cement, you have to be aware of rounding errors, right? If you get sloppy and you round these, if you make this like 19 and 7 and 8 and 67, well, it won't add up to 100 for starters. But if you make rounding errors and you start to multiply this by, thousands of kilograms, you might run into problems, right? With concrete, you might just get a really weird consistency and it doesn't flow right, right? With glass, you might get a really weird viscosity and it doesn't melt properly. If one of these elements provided color, you get the wrong color, right? Instead of light blue, maybe it's dark blue. You have to be aware of when you're going to batch together materials to make a recipe that you don't make rounding errors and add too much of something than what you thought you were going to or should, because the properties can be affected. So if you gave me like 1 decimal place off a point, because you'd also get addition errors where it wouldn't add up to 100. It's not hard to get it to add up to 100. You just have to pay attention to the numbers you're calculating. You could go out to 3 places, right? 4 places is probably not necessary, right? But on Excel it would be easier to do than by hand. All right, 2 or 3 places is typically significant here. It's fine. 0 or 1, you're going to get mistakes. All right, so this adds up to 100. The weight fraction, just take the weight percent divided by 100. All right, or just don't multiply it by 100 to begin with. So it's just moving the decimal point over 2 places. All right, so these numbers should be identical, except for the decimal point. All right. So this adds up to 1 to 4 places. This adds up to 100 to 2 places. Required batch. We want to make 3.3 kilograms. All right. So that is 3,300 grams. All right. This column was in grams. All And again, this was in grams. So how do we figure out how much to weigh now? Multiply. Multiply how much we want by each weight fraction, all right? And you get this. And again, watch the decimal places, right? If you're rounding these up and down, right? Again, that's going to be a significant source of potential experimental error, which again could create problems. So your 2 or 3 decimal places is adequate. 0 or 1, not so good, especially if it doesn't add up. It's very easy to get these to add up to what they should, right? You shouldn't be off by, 4, 5, 6, 20 grams, as some of you are, right? That's just being sloppy. Don't be sloppy, right? If it should add up to 100, figure it out, right? If it should add up to 3,300, figure it out, all right? It's not tough to do. It just takes a little bit of time, right? And going, okay, do I round that up or do I round that down? Do I go to 2 places or 3 places? All right, you can do your diligence to figure it out. All right, so this adds up to 100, this adds up to 1, this adds up to exactly what we want, right? The mark of being careful. Now, part B. It can happen that you don't have the exact material that you want, but you have something similar, right? So in the case of glass, maybe we don't have potassium oxide, but we have potassium carbonate, and we could substitute that, right? You can make substitutions in your recipe, in your batch. Potassium carbonate, when you heat it up, will decompose and give us potassium oxide and carbon dioxide, right? You can write it like this in the molar form or here in the chemical form. So it'll give us what we want, just with the addition of some carbon dioxide. The problem is the mass difference, right? We want a fixed amount of potassium oxide. If we weigh out the same amount of potassium carbonate, we're not going to have as much because we're going to lose gas. We're going to lose carbon dioxide, and we're going to get less potassium oxide. So we have to compensate. We have to weigh out extra to compensate for the gas loss. All right. So we need to know how to correct it. We need a correction factor. In this case, it's called a batch multiplier. All right, that's our correction factor, the batch multiplier. So determine the batch multiplier for potassium carbonate as a source of potassium oxide, and then determine how much of the carbonate we apply the required amount of oxide. We calculate in part A, right? So in this case with glass, it's common to make a calculation where everything is pure. And then we make additional calculations as a correction for impure substances, right? We have perfectly pure, and then we make a correction to use other materials, right? It keeps it simpler that way, right? And you might have similar logic in other batch processing like concrete. All right. So we need to figure out the correction factor. First, we need to know the weight fraction of potassium oxide in potassium carbonate. We do that using the molar mass. Easy numbers to look up, right? Look them up on Google or calculate them from the atomic masses, right? And I showed you examples of that. Molar mass potassium oxide, molar mass potassium carbonate, 94.2 divided by 138.21. Weight fraction, 0.682. Potassium carbonate is 60% potassium oxide, which means the balance of, what is that, about 32% is carbon dioxide. right? So this is only 2/3 pure. It's got 1/3 impurities. So that's what we need to compensate for. So now we have the batch multiplier, 1 divided by the weight fraction. The batch multiplier is 1.466. 1.466. You could get the same number by doing 138.21 divided by 94.2. But if I showed you that, it doesn't make any sense. It doesn't make any sense why the heck you would do that. All right. So you do it this way. Get the weight fraction. 1 over the weight fraction is the correction factor, the batch multiplier. All right. That's easier for people to follow. All right. How much? How much do we need now? All right. All right. Impure material mass is the batch multiplier times the pure mass that we required. All right. We wanted 610.5 grams. Back here. This is the pure amount. But we don't have that. We ran out. We have carbonate now. We want this much. We multiply it by the batch multiplier. That's why it's called a multiplier. And we get this, 894.99 grams, or maybe 895, all right, depending on how good your balance is. We would weigh out that amount to give us this much potassium oxide, right? Because we're going to lose almost 300 grams of carbon dioxide due to thermal decomposition. It's going to go poof, it's going to go away, taking its mass with it. All right. So this would be the summary, right? This is what you would batch in the laboratory. You had this molar formula. You converted it to this weight formula to make 3.3 kilograms of glass with 3 pure oxides and 1 carbonate. All right. All right, that's the end of that one. One more, and I think we'll be done for today. Worksheet 8. Worksheet 8. Polymers and composites. So this was a 2-part one. Polymers and composites. All right. So this was lecture, I don't remember what number, but it was on polymers and composites. All right. I gave you this for polymers. For many polymers, it's observed that the tensile strength, sigma sub Ts, is related to the number average molecular weight, so M sub n bar, by the following equation, right? Tensile strength is some infinite sigma minus A over number average molecular weight. So tensile strength at infinite molecular weight, that sounds logical, and A is a constant. Use the data in the table to determine the following. Show your work. So here's PMMA, polymethyl methacrylate. Tensile strength, 112, 174. Molecular weight, 75,000 grams per mole, 115,000 grams per mole. So we see at high molecular weight, we have high strength. Low molecular weight, we have lower strength. All right. So find from this data the values and the units, sigma infinity and A, whatever A is, and then calculate the values of tensile strength in MPa if the number average molecular weight is 55,000, so lower and then higher, 175,000. Right? So there's one up here and one down here. That should be low strength. That should be high strength. Right? That would correspond with what the 2 data points are showing us, which is basically a line. Right? So how do we solve for A? How do we solve for A? Right? We look at this. We don't know sigma infinity. we have sigma TS and M sub N. We have two unknowns, right? And we can't solve them just by trying to plug in numbers into one equation. One equation and two unknowns. Well, we can subtract. We can subtract, right? So we have 174 equals sigma infinity minus A over 115,000 minus 112 equals sigma infinity minus A over 75,000, right? We can subtract one equation from the other, right? So we have and we're subtracting, right? I don't know, I'm trying to draw an 8 there. Right, we can subtract that. And what happens is that unknown goes away, right? We subtracted it out. We don't need to know what it is. Yay. So 62 MPa equals minus A over 115K minus A over 75K. It reduces to this, and we get A. 13.4 times 10 to the 6th MPa grams per mole. It's a very awkward unit, right? Again, it's like the Hall-Petch equation. There's awkward units here. And if you start deviating, right, at first, you might make mistakes. And some of you did make mistakes here, which gave you incorrect answers. So again, when you're first learning things, try to copy the source, right? Copy how the source does it, assuming it's correct, until you understand it and figure out how it works. And then you could start to make adjustments, right? You can start to adjust things. And that way you'll know that something is right or wrong. I think, again, some of you, I think you played with this unit and you got some weird numbers and you didn't know it was quite wrong. All right. So when things are presented this way, it's often for a reason. Right? It's often for a reason. I mean, yeah, it might be able to be simplified somehow, but that might break something. Right? If you don't understand it, you don't recognize that right away. Right? Now, we solve for A, use one data point with A to solve for sigma infinity. All right? So again, here's our equation. Rearrange sigma infinity is sigma TS plus A over MN. 174 plus 13.4 times 10 to the 6th MPa grams per mole divided by 115,000 grams per mole. Look at that. Those cancel out. 174 plus 116.5, 290.5 MPa. All right, so that's sigma infinity. Or apparently what it's indicating as the maximum tensile strength for infinite molecular weight, which does not sound terribly realistic. Right? But often at the extreme ends of data sets, right? What is reality? What is happening? That's hard to comprehend a lot of the time. But we work in the middle. We don't go to the extremes in everyday use. So now solve for tensile strength at 55,000 grams per mole. All right. So from that data, we want to go to a lower molecular weight. We should expect a lower strength value according to the data. So 290, right? This is our maximum, and we're subtracting some value based on the molecular weight with this constant value. We get 46.9. Now what happens if we extrapolate here, right, to the higher strength, not the lower strength? So 175,000 grams per mole. All right, so again, higher molecular weight. Here's our little correction factor, 213.9 MPa. Again, this strength was lower, this strength was higher, approaching 290. And that corresponds with what we understand about the data in this equation. Right? So what you're seeing here is something like this. An empirical Flory equation relates various mechanical properties P to molecular weight M of a polymer with constants I and J. Right? This is similar to Hall-Petch behavior, which we see in metals and ceramics. Metals and ceramics have a grain size. Amorphous polymers don't have that. They have a molecular weight. They have a chain length. And it's observed that higher molecular weights often lead to higher mechanical properties. Right? So you have low density polyethylene, which is not that strong. You have high density polyethylene or ultra high molecular weight polyethylene, which has really, really, really high mechanical properties. It's really, really strong in tension and things like that. And so you'd see a graph like this, where you have tensile strength 1 over the molecular weight. You have sigma infinity. You have the slope A. And you have this, and you have these two data points, right? It's following a form like this, the Flory equation. So it may not just be tensile strength. It might be other mechanical properties that obey this behavior. And again, in a limited range, we might just assume it's linear, right? The extremes, it may not be linear, right? But in a small range, we can make that assumption that it's linear. All right, the second problem here. Use A, the Voigt model, and B, the Roos model to calculate the Young's modulus of a ceramic composite if the composition is 55 weight% silica, silicon carbide, 25 weight% zirconium oxide, zirconia, and 20 weight% silicon dioxide or silica. Use the information in the table below. Show your work. Again, a lot of you, if numbers magically appear, I don't know how you did it, especially if you got it wrong. You should always show your work. One, if you study something later, you know how you did it, right? And two, for my benefit, if you did something wrong, I know how you did it wrong, and I can make a note. If you just magically have numbers pop up, that doesn't do either one of us any good, right? For opposite reasons. So silicon carbide, zirconia, and silica. Young's modulus, 402, 233, and 95. Density, 3,200 kilograms per meter cubed, 5680, 2650. So we have two models, a Voigt model and a Roos model, right? Mechanically, you're looking at constant stress in the phases or constant strain in the phases, right? These models are used in other elements of engineering. You'll see them pop up in things like electrical engineering, stuff like that, right? So these are kind of general purpose models that we can apply to various situations, right? They represent, boundary models, all right, based on two separate assumptions, right? So for elastic modulus, it's the first modulus times the volume fraction, plus the second modulus times its volume fraction, plus the third modulus times its volume fraction, and so on. We could do this with 200 materials. It'd be silly to make that, but we could do it. And the Roos model, 1 over the composite modulus. A lot of you forgot that this was 1 divided by a number, and you came back with a really tiny answer, which made no sense. Is the volume fraction divided by the modulus plus and dot, 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 right? These equations use the volume contribution, right? In mechanical properties of composites, the volume contribution is what's important, not the mass contribution, right? What if I mix together materials with 2 very different densities, like tungsten and aluminum, right? It might be 90 weight% tungsten because it's so dense. But on a volume level, maybe they're equivalent, maybe they're equal volume fractions. It's the volume that's important, not the weight. And some of you neglected that. Some of you just used a weight fraction, which, if you're being lazy and the densities are very similar, that could work. The error might be very, very small, and you wouldn't realize it. But if the densities are very different, you will get dramatically different answers between weight and volume. All right. The key is the density. These are, in the grand scheme of things, kind of close. But if you had tungsten and aluminum, very different, right? That's also a good thing to learn, right? What are the little, tricks or things you can do to speed things up, right? With these, if you have very similar densities, you don't have to convert necessarily, right? But you only know that after making a few mistakes. So use the volume fraction. I didn't give you that. I gave you weight percent, right? You have to convert. You have to convert between mass and volume using density, right? A simple equation that you all know since you were in high school, basically. So calculate volume fractions. If we know the mass percent, we know the mass of an imaginary batch, right? We can use the mass percent to make any imaginary batch we want, right? So I'm going to create an imaginary or a fictitious 10,000 kilogram batch, because kilograms matches the density. I gave you kilograms per meter cubed. So I'll just make a big imaginary kilogram batch and convert that to volume. All right, it'll make the math a little simpler, especially if you're doing it on paper. All right, so we had 55 mass percent, 25, and 20. Let's make a 10,000 kilogram batch. 5,500 kilograms, 2,500 kilograms, and 2,000 kilograms. That's 10,000. All right. Now use the density to determine the volume of each component in the batch. All right, so we can get the volume fraction. All right. Remember, volume is mass divided by density. So 5,500 divided by the density of silicon carbide, 2,500 divided by the density of zirconia, and 2,000 divided by the density of silica. We get these volumes. We have 1 cubic meters of silica, 0.44 cubic meters zirconia, 0.75 cubic meters of silica, with a total 2.908 cubic meters. All right. So our imaginary 10,000 kilogram batch is almost 3 cubic meters, all right, of the powders. Convert that to volume fraction. Divide each individual volume by the total, right? It's the same with mass fraction, right? Mass fraction or volume fraction, it's all the same math, right? 0.589, 0.151, 0.26, right? Mass fraction. Some of you used mass fraction, right? Some of you used mass fraction, right? It was 0.55. What was the other one? 0.25 and 0.2. Yeah, these can be similar, right? They're similar, but they're not exact because the densities are different, right? So you're going to get an error. It might not be a large error. It might only be a couple MPa, but it's still an error. It's a fundamental error in your logic of applying the equations. I said if you're in a hurry and you don't want to do the math, the answer is close enough maybe, but it's still wrong. All right. So this is what we wanted, mass fraction. All right. Now it's possible to solve for the composite modulus. All right. So here's the Voigt model. Here's the Voigt model. We only have 3 terms. So we have silicon carbide, zirconium oxide, and silica. Modulus times volume fraction plus modulus times volume fraction plus modulus times volume fraction. About 297 gigapascals. All right, mixing those 3 together in those proportions. The Roos model, again, we only have 3 terms. Volume fraction divided by modulus plus volume fraction divided by modulus plus volume fraction divided by modulus equals 1 over modulus. A lot of you got to the tiny little number and you stopped. You had like 0.005 or something. I don't recall. This is 206 gigapascals. All right. Now, logic check. All right. How do we know that our numbers make sense? All right. You may not always be able to figure this out, but in this case, there's a few things we can do. All right. The Voigt model is the upper boundary. It should give us the larger number. The Roos model is the lower boundary. It should give us the lower number. 297 versus 206. That makes sense. The Voigt model is a bigger number. All right. Both answers should be between the largest and the smallest moduluses. Right. We have boundaries here. This is the largest, this is the smallest. We can't make a composite using these equations that are mathematically outside of those boundaries. It can never be more than 400 because we're mixing in things smaller. It can never be smaller than 95 because we're mixing in things greater than that, right? So this is an upper and a lower boundary. Our numbers were 297 and 206. They're in between that. So logically, we didn't violate those boundaries. One is higher than the other. That makes sense too, right? So that's how you can double check just quickly. Did I do anything silly, right? You know, if they were reversed or if one was like 1,000 or one was 0.005, you know that you made a mistake, right? You should always try to figure out how to double check your work logically, no matter what you're doing. What are the boundaries? How do I know it makes sense? All right, I told you that before with, you know, understanding realistic numbers. Density is always between like 20 and 1 gram per centimeter cubed for materials. Anything greater or lower is you're in vacuum or you're in the middle of a black hole, right? So there's always logical thought to engineering, right? Understand the logic so that you know when you've done something wrong or something doesn't make sense that someone gives you, right? You might have to look over other people's work. And how do you know if it makes sense, if it passes the smell test, right? The smell test. You understand the logic behind it. And you know that it at least is plausible. All right. All right. I think that is the end of the slides I had for today. All right. Good. I still have 2 worksheets to return to you. And so at the end of the week, Thursday or Friday, I'm going to return the rest of your worksheets, and I will have another meeting where I'll go over them and I'll mention the final exam. All right. Final start next week. All right. So I'll talk about that in a few days. All right. If you can't come to the meeting, that's fine. I'll make an announcement. I'll post about it, and I'll have a meeting, and you can watch the recording. All right. Are there any questions? Let me stop sharing. Wow. Classes dwindled down to the hardcore students. Are there any questions? Turn that off. Turn that on. Okay, I'll talk about the final in a few days, and so you could ask questions then. All right. If there are no questions, that is the end of today. That's the end of the lecture for today. All right. So let me stop recording.